Section 9.3, we're finally going to get to solve some differential equations. So it's a fun unit. We want to solve separable differential equations. And then there are linear separable differential equations, which you just do the same thing over and over again so you can memorize the pattern if you choose. If you don't want to, you can just solve it each time. And then we will solve mixing problems where the in and out rates are the same, which will make sense when we do them. So, a separable equation is a first-order differential equation in which you can separate your two variables into two parts. So your derivative, separable, so we say dy dx, can be written as a function of x times a function of y. Separate functions. So you don't have x's and y's playing together. Now, equivalently, you could write it as dy dx is equal to g of x divided by h of x, and they have the opposite signs, letters than I do, but that's okay. And then you can just kind of imagine rewriting it with differentials as h of y times dy and g of x times dx, which is what we actually do. And then we just integrate both sides of the equations. So we use the chain rule to justify this, because if we want the derivative with respect to y of the integral of h of x dy, then we just imagine taking the integral with respect to y's on the left-hand side and the integral with respect to x's on the right-hand side. But remember, this is a chain rule, so the derivative with respect to y of this with respect to y is equal to this derivative times dy dx is equal to g of x, a function with x's in it. Let's do one. Example 1. Dy dx is equal to x squared over y squared. So I'm going to think about multiplying both sides by y squared. Now remember differentials. Dy is equal to y primed dx. Y primed is dy dx. So if I throw an integral on each side, y squared dy dx, integrating with respect to x, is the integral of x squared dx. So I did the exact same thing to both sides. I'm integrating with respect to x. But then I look at this little piece right here. Well, that's equal to the differential of y. So this is just the integral of y squared dy equals the integral of x squared dx. Now, I know it looks like we're just cross-multiplying, and you can treat it that way. But you know deep down in your heart you're using this to represent the differential of y. It works. So now y cubed over 3 is equal to x cubed over 3 plus a constant. This is an implicit solution. You remember way back in Calc 1 when you learned implicit differentiation, you had your x's and y's all mixed up together. If you want an explicit solution, you have to get the y all by itself. So I had y cubed over 3 is equal to x cubed over 3 plus c. Now I know that when you integrate you have to add c. You don't have to do it on both sides, just once. And we usually put it with the x. So now I'm going to multiply everything by 3. So y cubed is equal to x cubed. Now I'm going to play fast and loose with c. I can multiply c by 3. I could write 3c, but since we didn't know what c was anyway, I'm just going to leave it as c. So y is equal to the cube root of x cubed plus c. Now it does matter that the plus c needs to live underneath the cube root. Now we want to find the equation that satisfies the initial condition. I'm going to label this as my explicit solution first. So I want y of 0 to be equal to 2. So if I put 0 in for x, I need 2 to come out. So 2 is equal to the cube root of 0 cubed plus c. So 2 is equal to the cube root of c, so 8 is equal to c. So my explicit solution, square root of x cubed plus 8. Let's look at the pretty answer. There it is. Yeah, I went through explaining how I could just use that arbitrary constant. It doesn't really matter. Okay, let's do another one. I'm going to pause and get prepared. I wrote down my differential equation. Now I'm pretty happy because my x's and y's are kind of already isolated over here. My y's all live below the fraction bar. My x's are all above the fraction bar. So I'm not going to bother going through the process of talking about differentials again. I'm just going to rewrite this with 2y plus cosine of y over here with the dy is equal to 6x squared over on the right-hand side with the dx. Easy. Now I'm ready to integrate, and it's not even hard to integrate. I get y squared plus sine of y is equal to add 1 to the exponent, divide by the new exponent, and 6 divided by 3 is 2 plus a constant. I'm going to leave this as an implicit solution because it would be really challenging for me to try to write that as y as a function of x. Okay, let's do another one. Y primed is equal to x squared times y. Well, I'm going to write it down as dy dx because that's just another way of writing y primed. And then dy divided by y is equal to x squared dx. Oops. That's the one I wanted. I wanted to get it a little more focused. That's better. Okay. Throw integrals on both sides. So this is the natural log of the absolute value of y is equal to add 1 to the exponent, divide by the new exponent, and add c. Implicit solution. We could call ourselves done. Or, if we want an explicit solution, we make each side the exponent of e, because e to the natural log of y is just equal to y. And then I have e to the x cubed over 3 plus a constant. That's equal to e to the x cubed over 3 times e to the c. Because remember, when you have e raised to this plus that, it's e raised to this times e raised to that. And this is just a constant. So I can call it a e to the x cubed plus 3. Now I have an absolute value here. I can make use of this a to make sure that it's positive, so we can just say that y is equal to e to the x cubed over 3. We use that constant to take care of the absolute value. And there's the pretty answer. Practice problems. I think you've got A on your own, so give it a try and we'll meet back and compare. How'd that one go? It was very similar to the previous one. We had x squared times y, and this one we just had x times the square root of y, which I went ahead and wrote as y to the 1/2 power. And then when I divided both sides, I went ahead and wrote it as y to the negative 1/2 power on the left-hand side. And then I add 1 to the exponent, divide by the new exponent, add 1 to the exponent, divide by the new exponent. I rewrote 1 over 1/2 as 2, divided both sides by 2 to isolate the square root of y, and then I squared both sides. Be sure that you put parentheses around because you have to square the whole thing. Now the next one, you're going to need to factor that denominator before you start trying to separate it. You can't look at that and say, oh, that's separable. But when you factor out down below, factor ut squared plus u to the 4th times t squared, it's going to work out. So give it a try and we'll meet back and compare. Did you make it? Let's look at it. So you factored the t squared out down below. You left that over there with the t's. You multiplied both sides by the u plus u to the 4th power. That side was easy to integrate. Over here, you had to think way back to Calc 1 where we divided it into 2 pieces because we have 2 terms on top, 1 on the bottom. So everybody gets to be divided by t squared. And then it's an add 1 to the exponent, divide by the new exponent. And since we have the 2 u's over here, I would not expect you to get an explicit solution for that. Implicit is fine. The next one, similar. You're going to have to manipulate it a little bit in order to separate it. First thing is pretty obvious. dz dt. You're going to subtract e to the t plus z from both sides. Then you're going to have to recognize laws of exponents. E to the t times, not plus, times e to the z. Because e to the t plus z is e to the t times e to the z. So now you have something you can separate, so go forth and solve. How'd that one go? So, once we got to this, we were able to multiply both sides by e to the negative z power. You could have gone ahead and brought the minus sign over there with it, then you could have skipped this step and gone directly to just e to the minus z, e to the t plus c. And then I natural logged both sides. Now you could have left it right here. E to the negative z is equal to e to the t plus c. That's an implicit solution. But since we only have one z, let's go ahead and get an explicit solution. So I natural logged both sides. So negative z is equal to the natural log of e to the t plus c. I can't simplify that any. There's no laws of logarithms to help me with that. So z is equal to the negative of the natural log, e to the t plus c. So let's talk about separable linear first-order differential equations. So if you have a first-order differential equation where you just have y primed is equal to some number k sitting next to y plus a number. K isn't 0 and b is a real number. It happens a lot in modeling. Y is the rate of change. Y primed of t is the rate of change, of course. K times y of t is the natural growth or decay rate, just like when we had the y primed equals k times y. That was the natural growth or decay rate in natural growth in section 1. And then b is the growth or decay rate due to external forces. So let's solve this general linear differential equation. Get myself a new sheet of paper. So I start out with dy dt is equal to some number k times y plus b. Well, I need to get all my k's on one side and all my t's on the other. So I have dy living on top of ky plus b is equal to just dt, because I divided both sides by ky plus b, leaves me with just a 1 sitting over there. So this I have to write as the natural log of the absolute value of ky plus b, but remember we had to u substitute. U was equal to ky plus b, so du was equal to k times dy. So this would actually be 1 over k times the natural log of the absolute value of ky plus b is equal to integral of dt is just equal to t plus a constant. So now we have natural log absolute value ky plus b is equal to k times t plus k times c, but that's just a number and we don't know what that number is anyway, so we could call it c1, we could call it k, we could call it, well, we wouldn't want to call it k. We already got one of those. We could call it b, we could call it a, whatever you wanted to. But I'm just going to rename it c. So now I have natural log is equal to this, so let's make each side the exponent of e, just like we done before. So we have ky plus b is equal to e to the kt times e to the c. Because this isn't our first rodeo, we know that this is equal to e to the kt plus c, and adding exponents is just the same as the same base raised to that exponent. So now ky is equal to, it's just another constant. I'll call it a to the kt minus b. So I subtracted b from each side. And now I'm going to divide everything by k. So y is equal to a over k e to the kt minus b. This is just a constant, minus b over k. Don't lose that. So let's compare. I have 1 over k, so I end up with, we redefined that as c, so y is equal to some constant times e to the kt minus b over k. Now, we can get rid of those absolute values just by absorbing it into the constant. So, anytime you have a linear first-order separable differential equation, and let's rewrite this here as y equals, I'm going to go back to c, e to the kt minus b over k. This is just some unknown constant. We don't know what it is. K comes from our original differential equation. B and k come from our original differential equation. So, if y primed is equal to k y plus b, then y is equal to c e to the kt minus b over k. You can memorize that, and then you don't have to go through and solve that linear separable differential equation over and over again. You'll often be given an initial condition, and then you can figure out what your C is. So, the current I of T in the electrical circuit shown below can be modeled by that differential equation. So I'm going to need to write that differential equation down on one line because it's separated on two lines, and that's annoying to me. So I have L times di dt is equal, plus R times I is equal to E of T. So let's look back. Y of T, or Y primed, equals KY plus B. I would really like to make this look like, so my L times IT equals, look more like that linear separable equation. So let's isolate the DI, dt. di dt, first I'll just subtract Ri from each side. So this is a function with just t's in it. So di dt is equal to minus R over L times I plus 1 over L times e to the t. So all I did was isolate my derivative. Now determine the solution when L is equal to 4, R is equal to 12, and my function of t is just a number, so now it's a linear separable differential equation. If I had t's over here, it wouldn't be linear, but since we have just a plain old number there, we're good to go. So di dt, R was 12, L is 4, e of t is 60, and L is still 4. And I have an initial condition, I at time 0 is equal to 0. This is an initial value problem. Remember, initial value problems consist of a differential equation and a condition. I've got all that. So that means that let's simplify it a little bit first. di dt is equal to negative 3I plus 15. So this is K, and this is B, because we made it look like y primed of t equals ky plus b. So I is equal to some constant c, e to the negative 3t minus b over k. So c e to the negative 3t plus 5. But we want I of 0 to be equal to 0. So 0 needs to be equal to c times e to the 0 plus 5. So 0 equals c plus 5. Negative 5 is equal to c. So I is equal to negative 5 e to the negative 3t plus 5. Easy enough. So when you can get it into this form, it's really simple to solve it. We'll look at mixing problems next. So a typical mixing problem, we have a tank with a fixed capacity, and it's filled with a thoroughly mixed solution such as brine, which is salt water. Solution of a given concentration enters the tank at a fixed rate. The mixture is then stirred and it leaves at a fixed rate. They could be the same rate or they could be different. If the rates are the same, then we get a separable differential equation. So if y of t denotes the amount of substance in the tank at time t, so if you're talking about salt water, then y would be the amount of salt. Then y primed is the rate at which salt is being added to the tank minus the rate at which salt is leaving the tank. Leads to a first order separable differential equation. It can be used for chemical reactions, drugs in the bloodstream, pollutants into a lake, etc. So, tank contains 20 grams of salt dissolved in 5,000 liters of water. Brine, salt water, that contains 0.3 kilograms of salt per liter enters the tank at a rate of 25 liters per minute. It's thoroughly mixed and then drains from the tank at the same rate. How much salt remains in the tank after half an hour? First, we need to write down an initial value problem. But in order to get that, we need a differential equation. Example 6. So y of 0, the amount of salt in the tank at the very beginning is 20 kilograms. So we've got our initial condition. The tank holds 5,000 liters of water. Brine that contains 0.03 kilograms per liter enters at 25 liters per minute. So dy dt is equal to the in rate minus the out rate. Start with the in rate. Is coming in at 5,000 at 0.03 kilograms per liter at a rate of 25 liters per minute. Well, dy dt needs to be in kilograms per minute. So let's write what we have here so that I end up with kilograms per minute. So I have 0.3 kilograms per 1 liter of water times 25 liters per minute. So liters cancel with liters. I end up with 25 times 0.03, so 0.75 kilograms per minute. My out rate is exactly the same, 25 liters per minute, but I have y kilograms in the entire tank, which is 5,000 liters times 25 liters per minute. Now I can cancel again liters with liters, and I end up with 25y over 5,000 kilograms per minute. So dy dt is equal to 0.75 minus, because it's in minus out, 25 over 5,000. So let's see, clear this out, 5,000 divided by 25, it gives me just y over 200. There's my differential equation. Here's my initial condition. But this is a nice, friendly, linear differential equation. K is equal to negative 1 over 200, and B is equal to 0.75. Make sure that doesn't look like a minus sign. So, y is equal to some constant times e to the negative 1 over 200t minus 0.75 divided by minus 1 over 200. Simplifying a little bit, I have e to the minus t over 200. Minus minus is plus, and 200 times 0.75 is equal to 150. Now I go back and I use my initial condition. Y at 0 equals c e to the 0 plus 150 needs to be equal to 20. So c plus 150 equals 20. C is equal to minus 130, so y is minus 130 e to the negative t over 200 plus 150. Let's see how we did. In and out, 200, and I end up with exactly that. And now I need to answer my question that I had at the very beginning of the problem, which was how much salt remains in the tank after half an hour. And since this is in minutes, I need to do y of 30. And it gives me about 38.1 kilograms. Fun stuff. Give this one a try. A tank contains 1,000 liters of pure water. Pure water, that means your initial amount of salt is 0. And remember, for purposes of other problems, if pure water is coming into the tank, then your N rate will be 0 because there's no salt or whatever contaminant coming in. But give this one a try, set it up just like we did the last one. This one was a little bit more complicated than the example that we did because you had to add two pieces together to get your N rate, because you had two pipes draining into it. One was coming in at 5 liters per minute with 0.05 kilograms per liter of salt, and the other one only had 0.04 kilograms, but it was coming in at 10 liters per minute. So you had to add those together to get your N rate. Luckily, your in rate and your out rate were the same, so the amount of water in the tank wasn't changing. That's the important thing that makes this a linear separable differential equation. So now we have our in rate, and our out rate was y over 1,000 with 15 liters per minute. So I wrote that as a fraction because I like fractions, and then I left things as fractions. If you wrote them as decimals, that's okay. And then I found that my leading coefficient, my C, had to be negative 30 over 3, and I didn't plug 6 in, I plugged 60 in for 60 minutes to find out the amount after 1 hour. Now, another interesting question you could ask is how much salt would be in the tank if they left this running for a long period of time. In other words, what is the limit as t approaches infinity of the amount of salt in the tank? So limit as t approaches infinity of negative 130 e to the t negative 3 over 200 t divided by 3 plus 130 over 3. So if we look at this, we have a negative exponent on our e, which means it's really down below the fraction bar, and big bottoms go to 0, so this limit is equal to 130 over 3 kilograms. So after a long time, we expect the amount of salt in the tank to stabilize at about 130 over 3 kilograms. So that's just another interesting question you can answer from these mixing problems and using differential equations. So, fun stuff. Go practice. You can do it.